Right, this particular section is all about chemical equations and how we represent atoms and molecules when we're writing out chemical equations. All right? So we're going to start with some basics and how we represent things. When we talk about metals in chemical equations, in most parts, because metals are more complex forms, so we think about aluminum foil as a big sheet of aluminum. We don't represent it as sheet of aluminum. We represent it as aluminum when it's a solid. Okay, so the most time, even though it's a network of weird metallic bonds, aluminum itself is going to be a solid structure. We're going to represent it as a single atom. Okay, even though we don't isolate this as atomic aluminum, the way the metal network works out is that it's going to act like single aluminum atoms whenever exposed to chemical reaction conditions. When we talk about nonmetals, many nonmetals show up in groupings. Okay? And that's things like, let's see, nitrogen, oxygen, fluorine, bromine, iodine. A lot of those come up in groups of two. Okay? You talk about phosphorus. Phosphorus shows up in groups of 4. Sulfur is generally represented as 8, or as molecular, or as atomic sulfur, because it shows up in these flowers called sulfur flowers, and that's where you get the 8 from, because of the nice little shape that they make. Okay? So a lot of the nonmetals take up that form. When you talk about carbon, carbon generally shows up as graphite, or carbon shows up as diamond, or carbon can show up as C60. Okay, which is known as the buckyball. And there's other different types of allotropes of carbon like that, but these are the 3 main ones. This one was discovered relatively recently, back in late 1980s, I think. But 1980s, 1990s is when this became exciting. And later in the 1990s, we discovered it wasn't so exciting, so not a lot of research is done with those anymore. But graphite and diamond, these are the allotropes, which means 2 different forms of this same element. Okay? These allotropes are the primary ones that we use when we're talking about general chemistry. Okay? Now we talk about noble gases. The noble gases are always going to be monoatomic. So anything like helium, neon, argon, krypton, all of these are monoatomic, and I've skipped this, but generally you want to represent them as the fact that they're being gases. Okay? Some of these up here are gases as well. Nitrogen and oxygen are gases at room temperature. Same with fluorine and chlorine. Bromine is a liquid. Iodine is a solid. Phosphorus is a solid. Sulfur is a solid. All right? So those are the major ones. Metalloids themselves generally represent metalloids singularly in their atomic form. So things like silicon, that's going to be a solid. Okay? Germanium, all those types of things generally represent them as solids. Okay? Etc. Okay. But now we get into the thick of things. Now we're going to talk about how to balance these equations. These are the basics of how we write these things out. Now we've got to write how to balance chemical equations when we encounter them. So when we talk about balancing reactions, we have to basically implement the law of conservation of mass. Okay? To give you an example, hydrogen and oxygen. So if I have H2 gas, and I react that with oxygen gas, what I'm going to get out is water here. Right? All 3 of these are gases. But if you notice, I've got 2 hydrogens on the left, 2 hydrogens on the right. So far we're balanced. But the oxygens here are not balanced. The oxygens on either side are not in balance. So I have to do something to this reaction in order to balance these reactions. Okay? I can't just do this. I can't put a 2 right there. Because if I do, I'm changing the nature of water. I'm turning it into hydrogen peroxide. That's not what this equation is about. We have to pay attention to the rules that we're following. Okay? And that is, if we're going to blow hydrogen and oxygen up together, they're going to generate water, not hydrogen peroxide. So if I've got hydrogen and oxygen here, I have to make sure that the mass on the left-hand side, or the number of atoms on the left-hand side, correspond to the number of atoms on the right-hand side. So I've got two hydrogens here. I've got two hydrogens over here. So far, so good. One oxygen, one oxygen. How do I solve that? Well, you could put 1/2 oxygen here. That would work, okay? But for balancing in general, we don't like using half numbers. So we're going to use nothing but whole numbers here, okay? And to get around that, the first thing that I do is I always take something that's a compound, something with more than one atom inside of it, and I put a number in front of it. So I'm going to put 2 here. What this now means is that I'm multiplying the number of hydrogens by 2 and the oxygens 4. So what I've got here now is 4 hydrogens and 2 oxygens. Okay? What I have over here is 2 hydrogens, and I've got 2 oxygens over here as well. So I have to now balance these. And the easiest way to do that is just to put a 2 in front of the hydrogen. That changes my 2 hydrogens to 4 hydrogens. 4 hydrogens, 2 oxygens, 4 hydrogens, 2 oxygens. Both sides of the reaction are now completely balanced. Okay? That's easy. So let's look at an example that is a little bit more challenging. Okay? So let's look at this one. Okay, barium hydroxide plus, you should go back to using a different color. Barium hydroxide plus perchloric acid. All right. When these two things react, what we're going to end up seeing is barium perchlorate. If I look at that correctly, yeah, barium chlorate or perchlorate, excuse me, and water. Give me my space system coefficients here. All right. Now in this case, I don't have anything that's atomic. So everything here is not in elemental form. We've got several different compounds that are interacting in this case. All right? Now how are these things going to work? First thing you should notice is patterns. Okay? I've got a lot of different atoms here. ClO4, barium, water, H, a couple of hydroxides. It looks like chemical soup. But what you should do is you should look at what similar parts are on either side of the equation. I'm going to change water over here so you see that a little bit better. Okay? I'm changing water here to HOH. Okay? Now I'm going to identify the different parts of the reaction that are up here. And what I've got OH here, I've got OH there, and I've got perchlorate on both of those sides. So I don't have to break either of these down. I can treat these as single molecules that are jumping ship from different parts of either side of the molecules. Right? So this hydroxide is going to pair with that hydrogen. Okay? So that goes to that. All right? And then the barium is going to pair with the chlorine. So I'm going to treat them in that form. Okay? So how am I going to balance this? Well, let's count up atoms on either side. So on the left-hand side, I've got barium. Okay, I've got one of those. I've got one oxygen or 2 oxygens here. A hydrogen. I've got 2 of those. I've got another hydrogen, and I've got a chlorine, and I've got 4 oxygens. Okay. And instead of breaking it down that way, I'm going to assemble these into molecules that haven't changed on either side of the reaction. If they change, I have to break them down. But they're not changing. So I'm going to adjust these so that I'm just treating with the molecules in general. I still have barium, okay? But now I've got hydroxide, because I've got hydroxide here, hydroxide there. I've got 2 hydroxides. I've got 1 hydrogen, and I've got perchlorates. I've only got 1, okay? On this other side, I've got barium. I've got hydroxide. I've got hydrogen, and I've got perchlorate. All right, and this time I've got 2 of these things. So how should I approach this? What I want you to do is I want you to pause the video right now, and I want you to think about how to approach this and how to try to solve this. Okay? The first thing that I would do is I would put a 2 over here with water. It's the simplest molecule. Okay? So now each one of those is 2. Okay? You might have a different approach. If your approach is different but we get to the same answer, yeah, it's a pretty good thing, right? You don't have to solve it any particular way. Okay? Whatever way you feel comfortable with. So now I have to get the H's equal on both sides as well as the perchlorates. I put a 2 here, and now everything on either side balances, right? I took something that looked very complex, and what I did is I simplified it by looking at common molecular ions on either side. So this double replacement reaction is actually relatively simple to balance. Okay, one more example. Now in this case, I've got what's called a combustion reaction. The combustion reaction, I've always got this generated. Carbon dioxide and water. If I'm generating both of those, it means that I've got a combustion reaction, especially if I'm burning them in the presence of oxygen. Okay? So what I'm doing right now is I'm burning something called hexane in the presence of oxygen. So let's look at hexane, okay? And we want to do some chemical accounting. So I've got 6 carbons here. I've got 14 hydrogens, and I'm going to have 2 oxygens. Okay? On the opposite side, I have much fewer as far as I counted atoms. 1 oxygen, I've got 2 oxygens, I've got 2 hydrogens, and I've got another oxygen. Okay? Now, how to balance this thing? Remember I said, look for the most complicated thing to balance first, and then go from there. Right? I've got 6 carbons here, and I've got 1 carbon over here. So what I'm going to do is I am going to add 6 carbons. How do I do that? I put a 6 there? No. You put a 6 in front of the carbon. All right? This 6 will carry out through the molecule. So now I've got 6 carbons. I've got 12 oxygens there, plus 1 on the other side. All right? So now I want to balance my hydrogens. Okay, I've got 14 here, and I've got 2 over there. So that's actually pretty easy. So 7. Okay? So now I've got 14 hydrogens here, and I've got 7. Let me change that. Let me just erase it for here. And I've got 7 oxygens. Okay? Total number of oxygens that I have in this system is 19. Okay, how do you make O2 into 19? Question is, you don't, right? We're looking for whole numbers. So I've got this entire thing set up. So what I want to do is I want to get this to a point where it's a whole number. So what should we do? Multiply it by 2, somebody say? Good, I can hear you through the computer. Okay. Put a 2 here. All right, when I put a 2 there, this changes to 12. This changes to 28. Okay? Which means that now I've got to change this 6. Now I'm going to change it to 12. So now I've got 12 carbons. Change the number of oxygens that I've got to 24. Wow, I've got a lot of atoms coming at us at this point. All right? But at this point, because I changed the hydrogens to 28, I changed this 7 to a 14. And now I've got an even number in the case of 38. Right? What's 38 divided by 2? Quick! 19, that's right. So now I can put 19 oxygens here. All right? This makes 38 oxygens on either side. At this point, everything is balanced. Oop, I forgot to put this. There we go. All right, now everything is balanced. This particular type of reaction is called a combustion reaction. I'm going to give you a trick for these because you're watching my video, and you should be patted on the back for watching my video. Anytime you've got something that's even in a combustion, some sort of hydrocarbon that's even, what you're going to get, in general, is 2 of those in order to make this balance. If it's odd, if the number of carbons here is odd, you won't have to multiply it by 2. Interesting little fact. I'm just full of these interesting little facts, right? Right. The best way to master balancing reactions is to practice them. So what I want you to do is I want you to go forth and look through the chapter and try the examples in the chapter, work through them, and then work through the problems in the back of this chapter on balancing reactions. Okay? You got to practice these things to master it.